during this intro part, our mics are hot, so you can talk, but they'll hear everything you say. So, and we already have James, the astrophotographer, logging in. This is our 137th episode of this particular program. So we've done a lot of them. Pekka from Stockholm, Sweden is here. Bergman Scooter, Aaron Thompson, Mick Whitaker is on. Cameron Gillis is on. He says, I'm waiting approval to get the ES backpack tent and weather station. I'll send you a note that you can give to your spouse, and that always works. So, my Moments of Zen says, howdy everyone from warm and windy north of Boston. Warm and windy, that's great. Beatrice Hines says, hello again, stargazers, greeting from Belgium. Well, we have a worldwide audience here. This is good. Thanks everyone for watching and chatting in.
There's a rhythm emanating from the sun to the edges of the solar system. Roughly every 11 years, our star ramps up to a turbulent state, expelling violent eruptions. After a peak, it calms down to a quiet phase before starting all over again. This is known as the solar cycle. This ebb and flow of solar activity affects the entire solar system, including spacecraft electronics and astronauts that can be affected by particle radiation if they're not sufficiently protected. Understanding the solar cycle is one of the oldest problems in solar physics, and now predicting it is more critical than ever as we venture to the Moon, Mars, and beyond. So here are ways we've learned about tracking it.
So welcome to the dome. Today we're gonna observe the sun and see if it has some sunspots.
Every morning when the skies are clear, Olivier looks through this telescope in search of sunspots. These are dark blotches on the sun that are the main source of solar eruptions. They appear and disappear on the sun's surface.
So we're not looking at the sun, in fact we're looking at the shadow of the instrument. Then we put the paper always at the same place, and then we can start drawing.
Olivier and a team of sun observers record the pattern of sunspots by pencil. The first known record of sunspots date back to around 1,000 years ago in China. After the invention of the telescope in the 17th century, routine observations were made. Today, sunspot drawers still use the same technique. While we've created satellites that can see the sun in much more detail in recent decades, drawing by hand keeps the centuries-long record consistent. The sunspot number record goes back farther than any other instrument, allowing scientists to analyze the sun's behavior over many, many solar cycles. Sunspot numbers are collected from observatories around the world and are averaged. During every 11-year cycle, the number of sunspots rise from 0 to a peak and then go back down to 0 again. Scientists use these numbers to determine when a new solar cycle begins and how active a cycle is. Solar maximum, the period of highest activity, can vary wildly from cycle to cycle. The more sunspots there are, the higher the frequency of solar storms of all types. Some that create aurora, and some that can affect power grids on Earth. But sunspot number isn't the only indicator we see. These numbers are often combined with other signs. At the beginning of each cycle, sunspots appear on the sun in the mid-latitudes for a brief few hours to days. At solar minimum, there are often days without any spots at all. As the sun becomes more active, sunspots form closer to the equator and can stick around for weeks to months. These sunspot patterns give clues to what drives the solar cycle, the twisting of the sun's magnetic field. Like Earth, the sun has a magnetic field with a north and south pole. But unlike Earth, the sun's magnetic field becomes extremely complex. This is because the sun is made of plasma, a charged gas that generates electric currents. As the sun rotates, plasma around the equator moves faster than near the poles, causing the magnetic fields to become stretched, elongated, and then twisted. Then kinks in the magnetic fields burst through the surface as sunspots larger than the size of Earth. As the solar cycle unfolds, more sunspots appear and the magnetic field becomes more tangled. At the peak of the solar cycle, the sun's magnetic field flips. The North Pole switches to the south and vice versa. The cycle then ramps down, ready to start a new cycle. Scientists can eventually see the result of this flip inside sunspots using satellites. This black and white image of the sun shows the magnetic field on the surface. Most sunspots appear in pairs. Like a magnet, one side is positive and the other is negative. After they form, they gradually disappear again, leaving behind remnants of magnetic fields that move towards the sun's poles. Eventually, each pole accumulates enough magnetic fields, forcing the sun's poles to flip at the peak of the cycle. Then, new sunspot groups appear with the polarities in the opposite direction. Scientists look for a consistent string of these new sunspots in order to declare the next solar cycle. But the transition between cycles is slow and messy. Cycles often overlap, creating freckles of old and new sunspots on the sun at the same time. Scientists can only determine we're in the new cycle when the number of new sunspots overtake old ones, which can be 6 months to a year after the new cycle has begun. While these spots give us a visible tracker, in recent years, scientists have discovered another signal that's hard to see from Earth. The strength of the sun's poles during solar minimum can help predict how active the next cycle will be. After the poles have reversed at the peak, scientists keep a close eye on it for the next few years. If the magnetic fields accumulated at the poles become strong during this time, it's likely the next solar cycle will be an active one. If the buildup is weak, the next solar cycle won't be as active. While we use these indicators to track the sun, predictions are still hard. After all, we've only had detailed satellite observations of the last 4 solar cycles, and scientists are still learning about what causes the sun cycle. So until we piece together those missing pieces, the sun, even with its 11-year clock, will continue to surprise us.
Well, hello, everyone. This is Scott Roberts, and this is the 137th episode. I keep thinking that's so amazing because I just said the other day it was the 136th episode. But I can't believe that we've done so many episodes of the OpenGOTO community. Today with me are some special guests. With me and Jerry Hubbell, we've got Barbara Harris out of Florida, Terry Mann in Ohio, and Connie Walker from Arizona. And they are all, these 3 women are iconic astronomers, very involved in our community, and it's a pleasure to have them on our program today. I'm really happy to have Barbara, you and Connie. I've wanted to have on this one of our programs for a very long time. So Terry is often with us. Terry and the Astronomical League have been really super in helping us promote educational outreach on these programs. Terry, why don't you introduce, I know Barbara and Connie well, but why don't you introduce them to our audience? And let's talk about the Astronomical League Live 4, which is going to happen tomorrow night at 6 p.m. Central. So,
yeah. Okay, Scott, thank you very much. And actually on Astronomical League Live event number 4, both of these ladies will be on speaking tomorrow night. So we're really looking forward to that. First, I know Connie needs to be at another meeting shortly. So Connie Walker is a scientist with NSF's NORLab for 20 years, and she's been working a lot with IDA, the International Dark Sky Association, a lot putting together programs with different teams on dark skies, public, probably a little bit of everything. Connie, how about if you kind of explain a little bit about what you do?
Sure, thank you. Well, again, it is varied, but one of the biggest programs you may have heard about is something called Globe at Night, and that's a citizen science program for anyone all over the world to participate in to actually measure the sky brightness where you live. And this, again, helps, just like with the sunspots. If you ever have taken sunspots measurements and drawn the sunspots, it is much better when you have a conglomerate of people from around the world to help you collect the data, because you can't do it as one person. You can't be everywhere. And so the level of light pollution is growing, as you all know, probably faster than our population rate is growing. And there's about 80% of the world that has never really seen the Milky Way arch overhead and be as glorious in its brightness as you could see from a dark site. So that is something that we're losing at a very fast pace, and something that we can all participate in by participating in Globe at Night, and also doing little things around your house to minimize the light going up, basically. And that's a discussion for tomorrow night.
Great.
Thank you, Connie. Yeah, and you know, being with the Astronomical League and being an amateur astronomer, I think we all realize how important it is to really try to help as much as we can with light pollution. Everything we do, you know, every time we go to a dark sky site, and how many of us have to drive miles to get to a dark sky site anymore, where maybe you used to be able to just go down the block or to a local park. Anymore, it's so hard And so we all have a hand in light pollution and helping control. And I am really looking forward to your talk tomorrow night too, Connie. It's been a while since we've sat down and talked, but I think many of us are involved with IDA as well as astronomy because they just walk hand in hand. So thank you very much for taking your time out to talk to us. I know you have a meeting. Please feel free to stick around, or if you need to go, totally understand. We will see you tomorrow night.
I look forward to it very, very much. Thank you.
Thank you, Connie.
Thanks, Connie.
And Barbara Harris is the next one. Barbara Harris is a retired OB-GYN physician. And she's always been very active in astronomy ever since I met her years ago too. Her imaging is gorgeous, but she does a lot more on the scientific end. And tomorrow night, Barb will be the keynote for the live event. And Barbara, how about if I let you kind of explain a little bit about what you are going to do? And we look forward to hearing it.
Hi. Okay, tomorrow's program, I plan to give a talk on using the Astronomical League observing programs as a springboard to have members of the Astronomical League do more science with their observing. And I plan to take a few examples of the observing programs and then expand them and teach people how they can use those programs to do more in citizen science.
Yeah, you're very active with AAVSO too. You have done a lot of workshops. You were talking earlier about doing a lot of Zoom programs and how active everybody has been and how much we've seen astronomy grow, or how many more people have gotten involved in astronomy in the last year, because it's amazing what we see.
Yes, variable stars are my main focus, and I will focus mostly on that program and other programs that can lead into serious variable star work. But there are other programs also in the Astronomical League observing program that I will show how they can expand that and get more involved in citizen science.
Well, I look forward to that too. We've got roughly, I think, about 85 observed programs, I do believe. So there's quite a few to pick from, and to see how to be able to do more science with our programs will be fantastic, because we have a lot of members that are really interested in more than pretty pictures and would like to like to advance a little bit more into a different area. So that will be very interesting too. I'm really looking forward to that. And tomorrow night, what we will do, we will have an update from Carol, and there will be announcements about our annual convention, Alcon. He will have an update for that and a couple other things that are going on within the league. We start at 7 p.m. Eastern Standard Time. And as I said, Connie Walker and Barbara Harris, those will be there along with myself and quite a few other people. So please join us tomorrow night at 7 Eastern Standard Time. If you can, we'd love to see you.
Yep, you'll be able to view them simulcast on all the channels that you're watching right now. So, certainly join them. There is a question from chat, Terry. Beatrice Hines from Belgium is wanting to know how she could join the Astronomical League.
That's fantastic. We are working more on our international presence. We do have international members. Go to astroleague.org and you will see membership there. Please click on that button and it should take you right to how to sign up for the league. If you have any questions, please go to the contact page, or you can contact me at secretary@astroleague.org. If you have any questions, any problems, we'd love to have you as a member. Like I said, we're reaching out more internationally, and it's amazing to learn more from other countries, to see how things are going there, what you are doing there. We'd love to add as many people as we could and bring them on the program too.
Great. It looks like Connie has to sign off now, so we'll see you tomorrow, so Connie. Thank you.
Talk to you then.
Yeah. Yeah. So, well, that's great. That's great. So our next subject here, Jerry went through this taxonomy of errors that can affect your astrophotography, and we talked about atmospheric seeing. We talked about a bunch of different things. I think it was like 20 different aspects that you had identified. But
right. It was at least 20,
right,
maybe more. Mm-hmm.
One of the things that Jerry often talks about at the Mark Slater Remote Observatory is how he doesn't use an autoguider, but he uses something called the Telescope Drive Master. And Jerry, as an amateur astronomer, has written software to enhance it, to enhance this device. Explore Scientific does sell this device, but I think it takes the performance of your mount to whole new levels, and it works on a lot of different mounts. So maybe Jerry, maybe you can tell us more about it. You're an expert on it. So
yeah, I was your first customer back in 2010,
right?
I think, for the device, and it's been 11 years now almost. So that's amazing. But I developed some software. I worked with Attila in Hungary. He's one of the developers of the device, and I worked with him on it. I did some investigation on how it was working and was able to determine some things that were happening with it and help them improve it. And it was really a great project to get involved with when I first got into the thing. And I think that's what helped me get hired by you also. Is that right, Scott?
Yes. It's part of it.
So yeah. That was my first foray into getting into the instruments like that. I'm gonna share my screen. I'm gonna get on the Mark Slater Remote Observatory so I can talk about it a little and show you how it works, show everybody how it works and what the performance is like. It'll take me about a minute or two to get on here.
Yeah, in the meantime, we've got somebody who wants to know what it looks like, so I will get the page and give them the link to what this looks like. To get into a Telescope Drive Master, you have to have a compatible mount. They're available for lots of different brands. You would be buying basically an instrument box that is the Telescope Drive Master itself. It's connected to a high resolution Heidenhain German, encoder that attaches with a special coupler that's machined and set up for your mount. And then there's cables that go to your drive corrector. It plugs in like a ST4 cable or an autoguider cable would plug into your mount.
Wouldn't you know it? Since we're trying to present this today, it's not allowing me to connect to the observatory right now. It's timing out. So
it's timing out.
I need to contact Myron. I don't think he's home right now.
Is there a customer service for the Mark Slater Remote Observatory?
Yeah, kind of.
I think
Myron.
You're the customer service, right?
Yeah, I'd have to drive out there if Myron's not available. So I can't get on it right now. It's just a shame. But let me see. I don't know if I've got any pictures or anything I can demonstrate really. So I developed some software that talks to the Telescope Drive Master. It gets the data off the encoder system, and basically what I record is something similar to what you have with PhD guiding, where you have the guide error graph when you're tracking a star and the corrections. I get the same kind of data off of the encoder system, the high resolution encoder. It's an incremental encoder, and I plot that in real time. And unlike an auto guiding system that corrects the mount about once every second or 2 seconds or 4 seconds, however people run it, the Telescope Drive Master actually corrects much faster at a five times a second. So it's unlike an auto guiding system that has a hard time correcting for little, for inexpensive mounts. You've got these little ticks and burrs and little things, defects in the gear system that cause these little spikes that are hard to correct with an auto guiding system, the telescope drive master will correct those to a certain extent because it's updating 5 times a second. So that's the capability there for the telescope drive master that you don't get with an auto guiding system. And that's what frustrated me the most about back in 2010 when I was doing auto guiding, the little spikes that were coming about because I couldn't afford an expensive mount. My first mount was basically a Skywatcher EQ6 mount, which cost me about $1,300 at the time. And that's all I could afford. But unfortunately, it wasn't perfect, of course, like any other low-end mount at the time. That was considered a low-end mount at the time. We've got much less expensive mounts available today that perform actually better than that first EQ6 mount because they have belt drives now and everything else. But back then, you know, the auto guiding system allowed these little defects to get through the to the image, and it was difficult and painful to watch. So that's why I was really interested in the telescope drive master. And it still does a good job today on we have it on a couple of our systems at the Mark Sladen Remote Observatory.
How many hours do you think you have on your telescope drive master now?
Oh, what's this thing? So the one that's been at the observatory, it's been there for 4 years now. And I would say we've probably got over, well, 600, 800 sessions probably. So we don't leave it powered up all the time like we do the PMC-8 controller. I leave that powered up all the time. That's got thousands of hours of power up time. Probably 20,000 hours. I don't know if it's that many. Maybe 20,000 hours it could have been powered up. But the telescope drive master's got probably well over 1,000 hours, maybe close to 2,000 hours on it that we've used it.
It's quite a bit.
Yeah.
It's quite a bit. Well, that's great. And you can use, if you want, you can still use an auto guider with the telescope drive master as well.
That's right. That's right.
Yeah. So while it's going to be handling right ascension for you extremely well, the TDM will, has a pass through for the declination correction. This whole system was made by a guy named Attila Madai, and it's made in Europe, but it's an excellent product. While there isn't adapters for every mount, there is for many mounts. And certainly I'm using one now for my G11 mount that I have. So
let me pull up I'm going to go to their website and pull up the document I created back then when I tested it, and I can kind of show what the performance is like when I first got it. So where's my browser? Oh, start over.
Barbara, how do you're still on, how do you, how are you guiding your mount? Are you doing any guiding, or do you I remember that you had a 16-inch Meade telescope.
Yeah, I have a 16-inch Meade, but it's on a Astrophysics 1200 mount.
Oh, that's a very nice mount.
Yeah, so I do auto guide if I'm doing a long time series of like 3 or 4 hours.
Sure.
I do, but half the time I don't auto guide at all. I don't really need to. But if I'm doing a long, like 4 or 5 hour time series, I do auto guide.
Right.
And my whole observatory I control with Maxim DL.
Okay.
But for some reason I haven't gotten great auto guiding with Maxim DL. So I use PhD guiding, and that's the only thing I use outside of Maxim. Everything else is controlled through Maxim DL.
I see.
Yeah, I like Maxim DL a lot too. I use that at the MSRO.
Yeah, and I do my photometry with it, my calibration afterwards, and my photometry with Maxim DL also.
Right. But PhD2 seems to be like the platform for,
It,
for
I know, for some reason, I just can't match the guiding that I get in Maxim with PhD2 guiding. It,
Mhm.
you know, I tried it to emulate the same settings, but for some reason, I just don't get the same results.
Mhm.
And one night I'll play with it. I could probably play with it and figure out. But I figure, why do I need to if PhD2 is there and
Already
it
doing
does
the
such a
job.
great job? And
Right.
so, you know, I don't want to waste time tinkering. I want to waste time gathering data. So
That's right. That's right. Yeah, Jerry and I talk about that a lot because, you know, once you have your setup done, you want to get it so tweaked to where, you know, I call it making the equipment, making it disappear, because you
I
want to go
know,
after the data, right?
yeah, you don't want it to get into the way of collecting your data. It needs to be in the background. You
Right.
turn everything on and you don't worry about what the equipment's doing. You
Right.
just want to collect your data.
That's
Mhm.
right. Yeah, that's why I like it, the TEM, because you don't mess with the auto guiding system at all. You just turn it on and just forget it, and it works great. So this is the paper that I wrote back in 2011 after I received my TDM from Scott. And I was able to do some measurements of the performance, treating it like a black box. You know, I didn't know how it worked inside, but I knew what the output should be like, and I knew what I was able to record it. I wrote some software to do the recording, and then I don't want to go over the details of the paper, but I wanted to show the performance, how it would work here with this graph on the last page.
Yeah, you give lots of explanation there.
Yeah. So this is what it looks like. So you can see this is what the EQ6 Pro mount. It's got fairly typical PE, you know, that's showing there. The E6 Pro, I think, had a 4-minute, if I'm not mistaken, has a 4-minute worm period. I think that's right. And so this has got several cycles in it, but once you turn it, so this spike is when I turned on, and I just flipped it on while I was recording. So it came on and started correcting the mount immediately. And I've got it set. I had it set. There's settings you can have, little switches on it that you can set the update rate or the sampling rate, and also the correction band. We call it the proportional band for the correction. It's plus or minus 1 arc second is the tolerance band for the correction when I first turned it on. And you can see that it's moving around here. Each line, each of these divisions on the y-axis is 1 arc second. Okay, so you can see it's bumping back and forth between 1 arc second. And I thought it was interesting because I determined early on that the control algorithm was really, typically you have control algorithms that are fairly decent, like one of the typical control algorithm is called proportional, integral, and derivative, PID control. And that proportional control means you basically correct the amount in proportion to the error value that you get. You provide an input to correct it. But this was what we call bang bang control. What I found was that what they were doing is they were letting it drift until it gets to the limit of 1 arc second, and then it would just push it back, the whole amount back to the center. It would push it back. It would not, kind of like the way PhD2 guiding does. If you got a tolerance when you set the correction to say correct anything over 0.2 arc seconds of error, and then it pushes it back immediately, and then it would come back and wait for it to do another measurement, and then it would push it back again. So that's kind of the way this was working. it would get to 1 arc second plus or minus and then push it back, and then it would keep driving it back until it got to the 0 point. And so you can see initially I had it set to the 1 correction per second, which is 1 hertz, and then plus or minus 1 arc second. You can see that it's moving back and forth in that range, plus or minus 1 arc second here. And then right here, I turned it, I made it better. I turned it to 5 hertz corrections and then a half an arc second. You can see it really smooths out there. That's kind of how it works.
Oh, yeah.
And there's none of these little spikes. There's, you know, the worst spikes are within 1 arc second. The RMS value is basically a statistical measurement of that noise, you know. And the 1 arc, and what I measured on my EQ6 mount was it was able to correct, let me see up the top here, I say it, so I talk about a 2 sigma tracking error correction. Okay, RMS value is a one sigma value, which is equal to actually this, I don't even think this is right. This is not right here. I just realized. So plus or minus 0.7 at 2 sigma is equal to plus or minus 0.4, 0.35, or just 0.35 in RMS. That's about what it is. And that's what I get in the G11 now. Also, I get 0.35 arc seconds RMS of correction, which is pretty darn good compared to an auto guiding system. Most people can't get much better than a half arc second, I don't think, RMS in auto guiding with PhD2 in a camera, because the problem is you got, not only do you have the mount noise, which the TDM measures, but you also have the sky noise. So when you're measuring the sky with the auto guiding system, you've got the scintillation of the star plus the mount noise, and that's always gonna make your result worse than what you could get if you're just measuring the mount by itself. And that's what we're doing here with the telescope drive master. Does that make sense?
Yeah, it does to me.
Yeah.
I have one. So.
Yeah. So think about that. Anybody that's doing auto guiding, you have 2 sources of error, not just one. You have the mount itself, which you're trying to correct, and then you have the sky, which is another source of error, which you're never going to get rid of. And then you have it gets worse because you're only sampling at so fast a rate, and you can't correct the gear noise as effectively as you could with a system like this. So
great.
Pretty good.
Great. Thank you. Thank you. Well, Barbara and Jerry, we're heading towards the end of our program, but what you're going to be covering science at tomorrow's event at the Astronomical League Live 4, and what in particular will, maybe you already mentioned it at the beginning, but what will your talk be about specifically?
Well, I'm basically going to highlight just a few of the Astronomical League programs, and just encourage people that if they complete these programs, they can continue and branch out from these particular programs and do real science and just continue with the program that they're doing. Yeah. And the majority of it is going to be the programs that involve variable stars, since that's my area of expertise. But I'm also going to talk about there's an occultation observing program, and a lot of amateurs contribute to science by doing occultations. There's a spectroscopy. I'm starting to get involved in spectroscopy. There's a spectroscopy observing program of the Astronomical League. Double stars. Most double star measurements nowadays are done by amateur astronomers, updating separations of double stars. So these are Astronomical League programs where instead of just working at getting your certificate and pin for those particular programs, you can just continue and branch out and do citizen science and contribute.
That's very cool. That's very cool. I am also working a little bit with the American Astronomical Society, and they are really trying to reach out to people to do pro-am collaborations. And so, I'm sure that once you're kind of schooled up with the Astronomical League, you might be able to take that next step and work directly with a professional. And there's a lot of programs in existence now, and there's going to be more coming. So I think it's going to be very cool. You mentioned spectrographic work. Do you have a spectrograph now, Barbara?
I have I just purchased one a few months ago, so I haven't gotten started yet. But I'm trying to think of what's, I can't think of
Is
its
it the
name.
Alpi? Is it the Alpi?
No, it's,
No.
oh, I can't think of the company now. He gave a talk with the AAVSO spectroscopy workshop.
We have a
Tom Fields? Is that who it
Tom
was?
Fields.
Yes, Tom
We-
Fields. So
We have a spectroscopic grating. Is that the one you're talking about? The grating that you have on your filter wheel?
you could add it to the filter wheel. It's the one that Tom Fields sells.
Mm-hmm.
So
It's a Patton Hawksley star analyzer.
yeah. So I purchased the Star Analyzer 100 and 200 because I have several different setups that I'd like to use it with. So I purchased both of those a few months ago. So I haven't started yet, but I would like to start doing spectroscopy.
I just put up the link for Tom Fields' RSpec website, so you can see the equipment and the software and all of that stuff. It's very interesting. And Tom has been, a real champion of getting amateur astronomers involved in spectrographic work. So that's very cool.
Yeah.
Awesome.
Yeah. And his software, I've played with the software already, so I'm eager to start taking spectra and.
Cool. It works really well. I've got several years of experience using his software and working with the spectral grading. We've got the spectral grading mounted on 2 of our stations at the MSRO that we do work with. They really work well.
Yeah, and AAVSO has been promoting spectroscopy because now, besides warehousing variable star photometry, they are starting to warehouse spectroscopy results too. So once you start gathering data, it can be submitted to the AAVSO just like your photometry results.
Yeah. That's cool. That's very cool because with through the spectrum, you can definitely dive into, dissect what's going on with the star and understand those processes. Can you also see any kind of Doppler effects in stars? Is that possible with amateur level equipment?
With the Wolf-Rayet stars, you can see the long, they've got a big redshift. And Tom actually has a couple of articles on his website that talk about you doing the Wolf-Rayet stars.
We'll have to get Tom on the program sometime to talk about it. That'd be very cool.
I know he's so enthusiastic, he can get anybody hooked.
I know.
So he's a great speaker and brings a lot of enthusiasm.
Yeah.
So he'd be a great speaker.
He speaks to lots of clubs. He's done hundreds of talks over the years, and we were able to spend a lot of good time with him 3 years ago at Star Parties. Remember, Scott? He came with us and hung out with us.
Yeah, he was up in
Golden State Star Party, or up in Oregon, wasn't it?
It was the one in Washington.
Washington, right? Yeah. Washington, up in the border, near the border.
Yeah. a lot of fun. A lot of fun. He's brilliant and engaging, and and he knows how. He makes analyzing spectra fun. I mean,
I know his enthusiasm is infectious.
Yeah.
I mean, so.
That's very true. Well, wonderful. Well, thank you, Barbara. Thank you, Jerry. And I look forward to seeing you tomorrow, Barbara. I'll be the guy behind the curtain broadcasting this. So, all right. So
you'll be the wizard.
The wizard. Yes, the wizard in the blizzard. Well, the snow's gone now, so.
Yeah, at the end of my talk, I love recommending books. So one of the books I'm going to recommend is this one.
Yeah, there you go.
There.
Oh, the
look at that one.
imaging. Yeah.
Oh, that's
Yeah.
cool. I appreciate
Right.
that, Barbara. That's
At
cool.
the end of every talk I give, it's one of the books that I recommend.
Oh, that's cool.
So did you enjoy that? I mean, it was awesome. That
Yeah.
Oh, good.
It's all written. I highlighted for me, and that one and The Sky Is Your Laboratory are the two that I recommend to people most.
Well, that's
Barbara,
good to hear. That's really good. I really appreciate that, Barbara. That makes me feel really good.
Yeah.
Yeah, I love books, so I have to leave with book recommendations. So,
Barbara, have you written any books on astronomy?
No,
Been into
no.
it for a long, long time. So
I know. My husband encourages me to do something like that.
yeah, I know you have at least one discovery under your belt. How many discoveries have you made?
Mainly that one Scorpii. But one of the advantages of doing citizen science, like for variable star photometry, I do pair with several professional astronomers. And so I have several publications with my name on them because you collect data that they don't have time to collect. And so if they do a paper and your data is included, your name's on the paper.
Right.
So I actually have more astronomy publications than I do medical publications. So
Oh wow.
Yeah. So it's rewarding, to do work and then have your work being used and being having your name published on those papers.
Right. Yeah.
Right.
Well,
Now, just for your information, Barbara, if you are interested in writing a book, I am actually the series editor for the Patrick Moore Practical Astronomy series.
Oh, really?
And for Springer, they recruited me about 2 years ago, almost 3 years ago now, to take over at that point. So if you're interested, actually, I've got Terry Mann's interested. She's working on a proposal with me right now on auroras for a book.
Yeah, I'd love to probably write a photometry book, photometry for amateurs. And
well, here's your homework, Barbara.
Yeah, if you're interested, get a hold of me and send me an email, and I can help you along with that if you like.
Okay.
I'm gonna send you my email.
Okay.
In the chat. It's just jrh@explorescientific.com.
Okay.
All right. Okay. Well, we'll let you guys go. We've got more excitement coming up tomorrow with we'll have our regular daily program on, and then we'll be We'll be with Kent Martz tomorrow with the First Light Chronicles. He's going to be going over more of the universe sampler from the Astronomical League, and then we are back on at 7 p.m. Eastern, 6 p.m. Central for Astronomical League Live 4, and Kent and I will be on the program, that program as well. So I think we're going to talk about astronomy or something. So.
Astronomy.
Yeah.
Really?
I wanted to do astrology, but they wouldn't let me.
Yeah.
So. Anyways, thank you very much, and we'll see you guys later. Thank you to the audience, and look up those links that I gave you there, and we'll see you mañana. And as our friend Jack Horkheimer always used to say, keep looking up. Take care. Yeah.
Okay. See you tomorrow.
Bye. Bye. Bye, Barbara.
Hi, I'm Steve from Pulsar Observatories in the UK. Just took time out of production just to say how excited we are to be dealing with Explore Scientific as our new American distributor and partner. We've been making observatories for over 20 years. We're over 1,000 to our name and still growing. Products still evolve, but we still think that we have an unbeatable astronomical product. These domes really do take your hobby to the next level. They're fully automatable, fully ASCOM compliant, so it works with third-party software. They keep you out of the wind chill. They reduce dew and ambient light. They really do enable you to take your hobby to the next level. So we're really excited for the future. We know Explore Scientific will do a great job of our amazing observatory domes, and we look forward to seeing you soon. Thanks very much.
We're going to talk about the problem of drive errors in telescopes. All telescope drives have some sort of tiny drive errors. In a telescope mount like the G11, it has plus or minus 5 arc seconds of periodic error, okay, which means every turn of the worm, it can move a star 5 arc seconds one way and 5 arc seconds the other way. The way to correct that might have been through an auto-guider camera, okay? But a better way to correct it is actually watching the drive errors from the polar shaft. And that's what we're doing here. We have something that is a high resolution encoder here. And then we make that high resolution encoder send signals down to something called the telescope drive master. The telescope drive master is an ingenious little device. It gives instantaneous drive corrections so that we can take this plus or minus 5 arc second drive and make it practically zero, okay? So virtually no drive error, which allows you to not have to have a guide scope, okay? And to make perfectly round stars in your images. Telescope Drive Master sends instantaneous signals down to the PMC-8 control box in the same plug that we would plug in the auto-guider port. And at that point, it's a very simple system. Virtually, there's no setup. You just turn it on and it works. For more information, you can go to explorescientific.com and look under the mount section for the Telescope Drive Master. If you need more, if you have questions, give us a call at 866-252-3811 or chat with us live.